Hello everyone, my name is Mariella Särestöniemi. I'm a postdoc researcher from Center for Wireless Communications, Faculty of Information Technology and Electrical Engineering, University of Oulu, Finland, and also from Research Unit Medical Imaging, Physics and Technology, Faculty of Medicine, University of Oulu. Now I'm going to give you a presentation on our paper, a preliminary study on RF propagation for high data rate brain telemetry. And this has been done as cooperation with Professor Pomalaza-raez from Purdue University, Dr. Kamran Sayrafian, National Institute of Standards and Technology, Professor Teemu Myllylä, and Professor Jari Iinatti from University of Oulu. Here you can see the outline of my presentation. So first introduction, some background and motivation for this work. Then case study, I explain you the simulation model and antenna models. Then the simulation results consisting of power flow evaluations and radio channel evaluations. Finally conclusions and future work. So first introduction. As you know, there has been a growing interest in the development of non-invasive acute brain injury detection and also these continuous monitoring systems in recent years. So for example, this intracranial pressure and brain oxygenation monitoring and also like brain hemorrhage or stroke detection and so on. Additionally, this brain-computer interface, BCI applications, has drawn considerable attention because it's attractive and transformative applications across the many verticals in wireless communication fields. There are many requirements for this kind of wireless monitoring of brain signals. For example, low power, reliability, security, and of course, safety. Also, some of these BCI applications may require wireless link that can support high data rates reaching like 100 megabits per second. In order to meet these requirements, we should have deep understanding on the propagation in the brain area at various frequency bands before we can start developing and designing this kind of wireless brain telemetry systems. This wireless propagation inside the human body, in general in human body, at different frequency range, has been studied in recent years for all these frequency bands which are considered suitable for medical applications. So there are some papers on these topics, but only a few studies of these dedicated on brain implant communications or in general brain propagation studies. There are some papers, but most of these papers are based on simple tissue layer models. And these kind of tissue layer models are relevant for the applications where the brain implant is relatively close to the skull. But if we have the implant more deeper inside the skull or the brain, then we need more realistic human head models. So our aim of this study is to investigate RF propagation inside the human head at several frequency bands. And the novelty here compared to the other propagation studies is that we use more accurate computational model of the human head and also a directional on-body antenna which covers quite wide frequency band and allows evaluation these several frequency ranges which are considered suitable for medical monitoring applications. So this is the aim. So now we move to this case study and first about this simulation model. This study is carried out with Simula CSD Studio software, this three-dimensional electromagnetic software, which is based on finite integration technique. And we use there a Hugo voxel model. It's this kind of anatomical voxel model. And we chose this model because it includes brain tissue structure with separate grain and white matters, as you can see here in this crosscut of the figure. And here you can see the relative permittivity and conductivity values, so these dielectric property values, for the most relevant tissues in the head. here. And as you can see, there is quite much variation between the dielectric properties of different tissues. For example, brain's white and gray matters have quite different permittivity values as well as conductivity values. So that's the reason why it's important to use anatomically correct models, not just average models, if you want to study propagation deep inside the brain tissues. And then we move to the on-body antenna. We used a bi-directional biomatched mini-horn antenna, which is shown here in this figure. And this mini-horn antenna is originally presented in this reference by Blower and Giorgi. And it has been modified slightly to obtain better matching with this voxel-based head model here. Here you can see the dimensions. The height is 2.7 centimeters. D is 1.8 centimeters. So although it's directive antenna, it's quite compact size. Usually these directive antennas can be quite large because of these huge cavities they might need at those frequency ranges. So the antenna is composed of water-filled holes which mimic the frequency-dependent relative permittivity of underlying tissue over its entire bandwidth. And this biomatched mini-horn antenna has been designed to operate while it's tightly attached on the skin surface. And then these on-body antenna locations. We made evaluations in two different locations here in the side of the head, location 1, and top of the head, location 2. And these locations are selected due to their different propagation environment. At this location 1, there is quite thick muscle tissues called temporalis muscle layer below the mini-horn antenna, as you can see here, this muscle tissue. But in this location 2, there isn't such a thick muscle layer. And then also in this antenna location 2, which is just above the area where the left and right hemispheres are separated, there is this kind of great longitudinal fissure here. And here you can see the antenna reflection coefficients of mini-horn antenna at the locations 1 and 2. Quite similar, but some small differences. And then about this implant antenna. It's this kind of double ultra-wideband antenna, which is originally introduced in this reference by Zhang and Wu for capsule endoscope applications. It has cylinder shape with a size of 11 millimeters, 5 millimeters here. So now we would like to point that although this antenna might not be applicable for practical brain implant applications, it's capable to operate over large bandwidth from 1 to 6 gigahertz, and this will allow us to carry out this preliminary RF propagation study in this paper in the brain area. But for practical studies or practical applications, we would need, of course, antenna which is even smaller than this one, this capsule antenna. So now to the simulation results, and we will start with this power flow evaluations. So perhaps you remember that power flow is the time average magnitude of Poynting vector, and this Poynting vector represents the directional energy flux, so the energy transfer per unit area per unit time of an electromagnetic field. And here we express the power flow values in decibels, so that we have normalized so that the 0 decibels represents the maximum, so it means the value on the antenna here. And these figures present the power flow ranging from 0 to minus 65 decibels on the horizontal and on the vertical cross sections of the brain area at 950 megahertz, here A, 245 gigahertz, this B, 3.1 gigahertz, C, 4.0 gigahertz, D, and 5.8 gigahertz, E. And these figures correspond to the antenna location 1 of the mini-horn antenna. So it was here in the side. And then power flow values are evaluated in these locations A, B, C, D, E, and F here. And then we also show the power flow values in these tables. You can see here, by the way, the distance between the mini horn antenna and the location A, B, and C here in these centimeters. So maximum evaluated is here in the middle of the brain. It's 7.3 centimeters. So as we can see here in this 915 megahertz, we can get good coverage through the whole volume of the head with power flow values within this selected 65 decibel range. As expected, the power flow values decrease gradually from 35 decibels to 54 decibels as the propagation depth increases from A to 5. And then at 2.45 gigahertz, the power flow indicates good coverage, partially, like 75% of the head area here. And in general, this coverage decreases as the frequency increases. So here, maybe you notice that at point A, the power flow is power flow value at 940 megahertz is smaller compared to these values at 2.45 gigahertz and 3.1 gigahertz. So this is actually inconsistent with the fact that propagation loss is typically smaller at lower frequencies. So what is the reason for this phenomenon? The reason can be found from these reflection coefficients of mini horn antenna. At 2.45 gigahertz and 3 gigahertz, we have very good antenna matching here compared to this 915 megahertz. So this is the reason why also the power flow is not so good in this. But still, the values are good and can provide good communication link. Then we continued this study by making channel attenuation evaluations at this on-body antenna location 1, so that we set that implant antenna on those locations A to F and evaluated channel responses on all those locations. And here you can see the results. Frequency domain channel responses S to 1 at location A until up to F. And now we assume that the maximum path loss, 65 decibel, is tolerable in order to maintain reliable communication link. And we can notice that with that can be achieved at 940 megahertz, 2.45 gigahertz, and 3.1 gigahertz. So we can reach that with acceptable threshold. And then maximum attenuation for these frequencies at the locations F are minus 54 decibels, 58 decibels, and 63 decibels here. However, at 4 gigahertz, the channel attenuation is manageable until only at the implant locations A to D. These ones here. And implant locations A and F, the receiver with higher sensitivity would be required, as the channel attenuations at these locations are over 70 decibels. And here at this 5.8 gigahertz, only locations A and B experience channel attenuation within this margin, 65 decibel margin. So these results are aligned with the power flow observations discussed in section or the previous slide. And then the power flow evaluations on the on-body location antenna 2, here on the top of the head. So we made similar evaluations. And here we present the power flow on the vertical cross sections. Here it was more meaningful to present the cross sections in the front and on the side, these vertical cross sections, to observe whether these phenomena, and again same frequencies as previously. And here you can see the power flow values in these locations A to F, and also the centimeters. So as we can see, the tendency is quite similar as in the antenna location 1, also in the case of this power flow values at these frequencies. However, we also noticed that in this antenna location 2, the power flow values are generally at higher level compared to the antenna location 1. And this is mostly due to the existence of this temporalis muscle layer. So you remember this thick muscle layer, which we had in this antenna location 1. And also because of this area where the left and right part of the brain's hemispheres are separated. So it is also one reason why we don't have so bad power loss in the antenna location 2 as in the antenna location 1. So also we noticed an interesting phenomenon at 5.8 gigahertz here at the locations A and F. Here we can see that these locations are closer to the center of the brain, but the power flow values at these locations are increased, so they are at higher level, although the propagation depth from the on-body antenna is higher. So what is the reason for this? One possible explanation for this phenomenon is the existence of alternative path of the radio waves, which can arrive these points. And as you can see here in this figure, especially here, there is a stronger flow through the nasal cavities, as you can see here, in this 5.8 gigahertz. We don't see that phenomenon in these lower frequencies. So that could be one reason for that. So it like make a secondary route for this propagation. But this is the this kind of observation. We need to study this more in detail and see also what happens at the higher frequencies. Can we also see there this kind of alternative path, which make it the power higher inside the brain tissues. So now we ended this presentation by conclusions and future work. So these simulations results discussed in this paper suggest that the reliable communication link between the properly designed on-body directional antenna and the implant, which is located deep inside the brain area, can be achieved from 940 MHz up to 3.1 GHz. But beyond those frequencies, communication depth may be limited. But of course, when we have smaller communication depth requirement, we can use higher frequencies easily. And of course, these higher frequencies have their own benefits. So like these higher data rates or better resolution and so on. Also, our evaluations pointed out that the impact of the on-body antenna location on the propagation depth. So we could achieve better propagation depth with the antenna location 2 than antenna location 1. And then we also found this interesting phenomenon that the power flow values in the middle of the brain at 5.8 gigahertz were a little bit higher. And that was assumed to be because of due to the existence of this secondary propagation path in the nasal cavity. But these need more studies. So this preliminary study provided some insight into RF propagation inside the human head. But of course, more application-specific research is needed to better understand and characterize the propagation media. And of course, we need more custom-designed antennas, which consider regularity and safety issues, as well as SAR limitations. All these factors will impact the achievable propagation depth at frequencies. Our next aim is to verify these simulation results with the measurements results, which are done with the properly designed head functions for this frequency range. Thank you very much for your attention. If you have some questions, you can ask now or send me email to this address. Thank you.